Hey everyone, so in this video we're going to continue talking about numerical summary measures. And if you have not seen part 1, please go do that. Otherwise, let's just get going here. So here's a review from part 1, just as a refresher. Remember the sample mean, which we denoted by x bar, is the average of n values from the sample. So remember we just added up all of our data values and then we divided by the number of data values that we had. And we came up with the average, or the sample mean. The sample median, remember we denoted this by x tilde, is the middle number when the values from the sample are sorted from smallest to largest. So remember the first step when we were finding the median was to sort the values from smallest to largest, and then we looked for the middle number. If there was one middle number, we used that as our median, and if there were two middle numbers, then we took the average of them, and that is what we used as our median. We also talked about what's called skewness, and skewness refers to the lack of symmetry in a distribution of data. So for example, down here, we have a right skewed distribution. And how do we know it's a right skewed distribution? Well, the tail of this distribution is off to the right. So we would say this is a right skewed distribution or a positively skewed distribution. Just like over here, the tail of this distribution is on the left, so we would say this is a left skewed or a negatively skewed distribution. And finally, in the middle here, if it doesn't look like it's skewed in either direction, and if we can kind of draw a line down the middle of this and it looks kind of the same on the left and on the right, then we would say it's a symmetric or a symmetrical distribution. And then we tied all three of these concepts together, the mean, the median, and the skewness. We tied them together in the salary example. Remember, we had a room of people who were roughly kind of close to each other in salary, and then we had a surgeon who makes way more money than everyone else walk into the room. And that was the addition of an outlier. And then we observed what happened to the mean and the median when we added this outlier to our data. So remember, the mean was much more sensitive to this change than the median was. And we say the mean is much more sensitive to outliers than the median is. In other words, the median is much more resistant to outliers than the mean is. So you might be wondering, all right, so which one do we use? Do we use the mean or do we use the median? And the answer isn't quite so clear cut, unfortunately. It kind of depends on whether or not your distribution is skewed. So when your distribution is skewed, we generally want to be using the median. And why is that? Well, if you think back to our salary example, remember when we added the surgeon's salary, the mean increased all the way up to $84,000. And if you look back to the example, you'll see that $84,000 was more money than everyone in that room made except for the surgeon. So do we really think that's a good measure of center? And the answer is no. I mean, it's probably better to use the median in that case because the median is probably going to be more representative of the bulk of the population than the mean when the distribution is skewed. But when we have a symmetrical distribution, we want to be using the mean. And it's like, well, why can't we use the median? It's like, oh, you could use the median if you want. It's going to be pretty darn close to the mean when the distribution is symmetrical. But the nice thing about the mean is that it's mathematically easy to work with. So if we have a symmetrical distribution like this, we're going to be wanting to use the mean as much as possible. And we'll see a lot of examples of this throughout the course. And then the last concept we talked about is modality. And modality refers to the number of modes or peaks in a distribution of data. So if it had one peak, it would be unimodal. If it had two peaks, it would be bimodal. And if it had more than two peaks, we just called it multimodal. So for example, all three of these distributions down here are going to be unimodal. And for the most part, for the remainder of this course, we're going to be working with strictly unimodal data. So now let's talk about part 2. So we covered measures of center, we covered mean, we covered median, and those are very important, but we're also often concerned with measuring the spread of a data set. And some examples of these measures of spread include range, interquartile range, variance, and standard deviation. And we're going to be talking about all four of these in this video. So let's start with the sample range. And the sample range is fairly easy to calculate. All we need to do to calculate the range is to take the largest number of a data set and subtract the smallest number of a data set. It's basically the distance between the smallest number and the largest number. So let's look at an example. Suppose we have a data set with these values right here, and we could just look at it and say, okay, 1's the smallest value and 9 is the largest value. But just to make sure we're not missing anything, it's often helpful to sort the values from smallest to largest. So when we do that, we have this, and then we'll notice that the smallest value is 1 and the largest value is 9, just like we suspected. And so we have a max of 9, a min of 1. So the range, all it is just 9 minus 1. So our range is 8. So the nice thing about the range is that it's really easy to calculate. You take the largest number and the smallest number, and you find the difference between them. But the problem is that it's not very easy to work with, and it's often not very useful. And this is where interquartile range comes in. The interquartile range uses the same concept as the range, but only with the middle 50% of the data set. And we'll find out why this is useful in a little while. Interquartile range, or IQR, is defined as Q3 minus Q1. And Q1 is known as the first quartile of the data set, and Q3 is known as the third quartile of the data set. And what does that even mean? Well, let's look at a picture. So if we have our data set here, if our data set is this rectangle here, and we wanted to locate where Q1 and Q3 are, it's helpful to know where they are relative to the min and the max. So the min is going to be all the way on the left here. This is the minimum value of our data set. This is the lowest value in our data set. And the max is going to be all the way over here. This is the largest value of the data set. And the middle value, remember when we sort the data from smallest to largest, the middle value is going to be the median. So that's what this x tilde is in here. Q1 and Q3 are right in between each of these. So Q1 is what's right in between the min and the median, and Q3 is what's right in between the median and the max. So in other words, you could say Q1 is the median of the lower half of the data set, and Q3 is the median of the upper half of the data set. And if we want to get a feel for the difference between IQR and range, we can look at down here. This middle rectangle, the length of this middle rectangle is going to represent the IQR. It's the distance between Q1 and Q3, whereas the range is going to be the distance between the min and the max. And you might be wondering, well, why wouldn't we want to use range? IQR is only concerned with the middle 50% of the data points. Well, the reason why we don't want to use range here is because the range includes all the outliers. And if we're trying to get a feel for the overall spread of the data set, we don't really want to include outliers because outliers could really distort our view of how spread out the data points are. If we have all these data points that are really close together, and then we have one crazy outlier way off in the middle of nowhere, then it makes it seem like the data points are really spread out when in general, most of them are not. So we use IQR because it's a lot less sensitive to outliers than the range. And by the way, I don't have it listed here, but this is actually called a 5-number summary, if you've ever heard of that. If you list out the minimum, the first quartile, the median, the third quartile, and the max, that's known as a 5-number summary. So if you ever hear of a 5-number summary, that's what they're talking about. All right, so let's look at an example. So suppose we have a data set of these values right here, and we want to calculate the IQR of this data set. So first thing we need to do is we need to find where the median is first. So remember, the first step that we do when we're looking for the median is we have to sort the values from smallest to largest. And when we do, we have this right here. And you'll notice the middle of the data set is right here. So remember, when we're calculating Q3 and Q1, we need to find the median of each of these halves. So the median of the first half of this data set is going to be Q1. So that's going to be 3, which is what I have in red here. Similarly, the median of the second half of this data set right here is going to be 9, which I have in green. So Q3 is going to be 9, and Q1 is going to be 3. So as a result, the IQR, remember, is just Q3 minus Q1, which is just 9 minus 3, and that's going to be 6. So let's look at a slightly more difficult example. So suppose we have a data set with these values, and we're asked to find the IQR. So remember, like before, the first thing we have to do is sort the values from smallest to largest, because we want to find the median first, because finding the median first makes it a lot easier to find Q1 and Q3. So when we do that, we'll find that the middle of the data set is right here. So if we were looking for just the median, we would say, oh, it's right there, it's 7, nice and easy. And that's true. But now it makes things a little bit more difficult, because now you come up with the question, well, you're splitting the data in half, and you have to find the median of the first half of the data set, and you have to find the median of the second half of the data set. But do you include 7 in the first half, or the second half, or both, or neither? And the answer is, since 7 is part of the data set, then we're going to include the median when we're calculating our IQR. So what this means is, this is going to be the first half of the data set. So the median of the first half of this data set is going to be the average of 3 and 4, just like we did with the median example when n was even. Similarly, we're going to include it also in the second half of this data set. So we need to find the median of the second half of this data set, including 7. So in this case, it's going to be the average of 9 and 10. So just like I say down here, Q1 is going to be the middle of the first half of the data set, which includes 7. That is very important. So Q1 is going to be the average of 3 and 4. I have those in red up here, and that's going to be 3.5. Q3 is going to be the middle of the second half of the data set. Again, this is very important that we're including 7 in this. So Q3 is going to be the average of 9 and 10, which I have in green up here. So Q3 is going to be 9.5. So there we go. We found Q3 and we found Q1, and now we can calculate the IQR. So the IQR is going to be Q3 minus Q1, just like before. We found that Q3 was 9.5, and we found that Q1 was 3.5. So our IQR is going to be 6. So the important thing to note here, since this is what trips up a lot of people, is that we were including 7 here because it was part of the data set. Whereas in the last example, we did not include the median. The median in this example was 6.5. We did not include the median in this example because it wasn't actually part of the data set. 6 was part of the data set, 7 was part of the data set, but the median itself was not. Whereas in this example, the median was actually one of the numbers in the data set. So we are going to include that in the first half and in the second half. So we need to make sure we're careful of that. So let's look at another example of a measure of spread that's very common, and it's called the sample variance. And the sample variance is denoted by s squared, and we'll see why it's denoted by s squared in just a second. But let's look at what this formula is saying here. It looks a little bit scary, but Let's kind of take this piece by piece to see what's going on here and try to make sense of it. So first of all, we realize that we're summing something. And what are we summing? Remember that xi corresponds to each of the data points. So we look at the first data point, and then the second data point, and then the third data point, all the way up until the nth data point, the last data point. And what we're doing is we're subtracting the mean from each of those. So what does that actually mean when we're doing that? So if the first data point, for example, was 8, and the sample mean was 5, what would we be doing if we subtract 5 from 8? We would get 3, and that means that this data point is 3 away from the sample mean. So what we're doing when we subtract the mean from each data point, we're getting an idea of the distance between each of those data points and the mean. And then after we get those distances, we're going to end up squaring them. And there are a couple reasons why we want to square these distances, but the main one that we should probably be focusing on for right now is that it makes all of them positive. And we want these distances to be positive because, well, they're distances. So, for example, if you're standing 2 feet away from a car and then you walk over to the other side of the car, you're still going to be 2 feet away from the car. You can't really be negative 2 feet away from the car. So they're distances, they always need to be positive. And then the other thing too is that if we didn't square this and if we left this as it is, then this whole sum would add up to 0, which would make everything in this formula 0 all the time. So you're just going to have to trust me that squaring these distances is the best course of action here. So after we calculate each distance and square it, we're going to add them up and then divide by n minus 1. And this actually, to me, is the more intuitive formula here because we could actually see what's going on in this whole thing. We're taking each data value, we're subtracting the mean from it to get the distance, we're squaring those distance, and then we're taking the average of those squared distances by dividing by n minus 1. And you might be wondering why we're not dividing by n, but that's just a conversation for another time. It's a little bit too complicated to be talking about right now. You're probably just going to have to trust me on that one for right now. But I say this is the more intuitive formula because there's actually another way to calculate the sample variance. This is actually equivalent to what's up above, but this one to me looks a lot more complicated. However, this is actually known as the shortcut method to calculate the sample variance. And why is that? Well, what's common in statistics courses is these two quantities, the sum of the x squareds and the sum of the x values, are going to be given to you. And if you know them in advance, then this formula is a lot faster than this formula up here. The only problem that I have with this formula down here is that you can't really intuitively see what's going on like we can up here. You could very clearly see that these are distances right here, but down here, you can't really see what's going on. It just looks like a bunch of sums and squares and ends, and it looks a little bit messier. So depending on what information you have available to you, you might want to choose to use one formula over the other, depending on your situation. And then finally, sample standard deviation, which we denote by s instead of s squared, is just the positive square root of the sample variance. So if the sample variance is 9, then the sample standard deviation is going to be 3. So like we mentioned, the sample variance and the sample standard deviation tell us how spread out the data values are. They're measures of spread. So how do we interpret them? Well, when the sample variance and the sample standard deviation are low, it means that the data values are close together. It means they don't vary by a whole lot. They're all grouped together in the same place. And conversely, when the sample variance and the sample standard deviation are high, it means that the data values are very far apart. It means that the data set has high variance. It means that the data points are very spread out. They vary a lot. So let's look at an example. So we're going to use this one example where we're going to calculate the sample variance and the sample standard deviation using both formulas. So we have a data set with n equals 5, meaning we have 5 data points, and these are the values. And we're asked to calculate the sample variance and the sample standard deviation. So if we're going to be using the first formula, let's look back at that. If we're going to be using the first formula, then we need to calculate the sample mean in order to be able to plug it into the formula. So let's take care of that first. So to calculate the sample mean, remember all we need to do is add up each of the data points and then divide by the total number of data points that we have. So it'd be 3 plus 5 plus 8 plus 10 plus 4. And then if we divide that by 5, because there are 5 of them, then we would get 30 divided by 5, which is 6. And then we can use this in the formula. So let's plug these into the formula. So remember, this was our formula for the sample variance. And remember, we already know what n is. We know n is 5. And we already know what the sample mean is. The sample mean is 6. So we found those out. So all we really need to plug into this formula are each of the x values. So let's take it one by one. So remember, our first data point was 3. We need to subtract the mean from 3 and then square it. So here we have 3 minus 6, and then we're going to square that. And then the next data point was 5. Then we do the same thing with 5. So we're going to take 5 minus 6, and then we're going to square that. Then we're going to do 8 minus 6, then we're going to square that. 10 minus 6, we're going to square that. And then 4 minus 6, we're going to square that. So we're taking each of the data points from our data set, 3, 5, 8, 10, and 4. We're subtracting the mean from them, and we're squaring each of those distances. And then after we square those distances, we're going to add them all up. So that's what this sum is telling us to do. We take each of the distances, we square them, we add them up, and then after we do all of that, we come up with this. We come up with -3 squared plus 1 squared plus 2 squared plus 4 squared plus -2 squared. So this is an example of we have negative distances and we need to make them positive by squaring them. So when we add all of these up, we get 9 plus 1 plus 4 plus 16 plus 4, and we get 34 for this whole sum in here, and then we need to divide that by n minus 1, which is 4. So if we do that, we get 8.5. So again, all we did was we took each distance, we squared it, and we added all of them up, and then we divided by n minus 1, which is 4. And in this case, we got 8.5 for our sample variance. So now we're going to calculate the sample variance and the sample standard deviation of that same data set using the other formula. And remember, this was the other formula. Now, the two main obstacles when we're using this formula are going to be these two sums. This sum right here and this sum right here. So let's take care of those first because they seem to be the most complicated part of this problem. So to get the sum of the squared x's, we need to take each of the data points and we need to square them and then sum them up. So remember our data points were 3, 5, 8, 10, and 4. So we're going to square each of these and then we're going to sum them up. So that sum is going to be 9 plus 25 plus 64 plus 100 plus 16. And we end up getting 214. So that whole sum, this piece right here, is going to be 214. And then with this simple sum, remember we've done something like this before. This is just telling us take each of these x values and sum them up. This is about as simple as the sum can get. Remember, our data points were 3, 5, 8, 10, and 4. So when we add these up, we get 30. And then now we've taken care of the two hard parts of this formula, and then we can just drop them right into the formula. So here again is the formula, and now I've highlighted the two sums that were giving us trouble before, right here and right here. And we just figured out what those were. We figured out that that red sum was 214 and that the teal sum was 30. So we could plug those right in. We could plug the 214 right here, and we can plug the 30 in right here. And now the other thing we know is we already know what n is. We know n was 5. So that's another thing that we can plug in. So after we plug everything in, we're left with this. There are no unknowns here anymore. We could just, this is just plug and chug. So after you do the math here, you take 30 and you square it, and then you divide it by 5, and you're left with 180 for this piece. And then you subtract that from 214, and you're left with 34, and you're dividing that by 4. And this should look familiar because this is what happened when we calculated the sample variance using the other formula. Now, the last thing I want to point out here is take a look at how easy this would be if these two sums were given to us already. Like I said before, in a lot of statistics courses, you'll find that you'll maybe walk through this formula one time, but after that, these two quantities are going to be given to you. So when these two quantities are given to you, it's basically saying, here's the formula right here. This 214 and this 30 are already being given to you. So it's pretty much just plug and chug from there. But if you don't have these quantities, it doesn't necessarily make it that much easier or that much more difficult than the other method. And since our sample variance is 8.5, we can now calculate our sample standard deviation. And remember, the sample standard deviation, S, is just the positive square root of the sample variance. And our sample variance is 8.5, and the square root of that is 2.9155. And that's going to be our sample standard deviation. So what's the benefit of using standard deviation instead of variance? Well, standard deviation allows us to express the spread in the units of the problem. So for example, if our data set was in terms of inches, we could say that on average, each value is 2.91 inches from the mean. And one thing to note here is that this is not the exact interpretation of sample standard deviation, but it's very close. So for right now, we can think of it that way. And then down here, we have a visual representation of each of those data points on a number line along with the sample mean, which in our example was 6. And what we're attempting to do when we calculate the sample standard deviation is to calculate how far on average each of these red points is from this big blue point. So I hope it makes a little bit more sense seeing it this way. But anyway, that's all for this video. I hope you enjoyed it and found it helpful, and I will see you in the next video. Take care.